In our discussion about capacitors, we've brought up multiple times that capacitors are really good at storing energy, specifically electrical energy. In this video, we're going to actually talk about how much electrical energy these capacitors can store. So, the amount of energy that a capacitor can store is equal to the work done to charge the capacitor, which we have found to be work is equal to Q times V. Well, here's a simple parallel plate capacitor in the figure on the left. What voltage do I use? Do I use the 20 volts? Do I use the 0 volts? Or do I use the one in the middle, 10, or some other value? What we're going to use is the average value, which of course is just the voltage on the parallel plate plus the voltage on the negative plate divided by 2, or 1/2 of the total voltage of the capacitor. Which in this case, for this example, the two plates are charged up to 20 volts. And since they're charged up to 20 volts, the voltage we'll be using is half of that, 10 volts. So our equation for work, or potential energy, then becomes the charge Q times 1/2 of the voltage of the capacitor. Well, that's great. So we can easily calculate the potential energy by taking 1/2 times the total charge on the capacitor. Multiply that by the voltage. Voltage isn't a problem, but how do you find the charge that's built up on the capacitor? Well, remember that earlier we defined capacitance as being able to solve this equation, that the capacitance times the voltage equals charge. Well, if I substitute that in, charge is going to equal CV, so 1/2 of CV times V would be 1/2 CV squared. So it's just, that's just a substitution to get this equation, substituting CV in for Q. Gives us just another form of the equation. That way you can find out how much potential energy is in a capacitor simply by knowing the capacitance and the voltage it's applied to. Similarly, if I take this same equation and I solve for voltage, then I get another form. That voltage is equal to Q over C. Then substitute that V in for my equation. I get that potential energy is going to be 1/2 of Q squared over C. Now these three equations all work for calculating the potential energy of a capacitor. The one you use will depend on the information you are given in your questions, in the problem you have to solve. If you're given charge and voltage, use the first equation. If you're given charge and capacitance, use the last equation, and so on. Now, when it comes to energy, sometimes we use something called energy density, which instead of talking about the total energy in a capacitor, you talk about the amount of energy per unit volume. You can think of this, you have a great big huge sheet. I'm not even going to try and draw this three-dimensionally. So you're looking at this sheet from the side with some dielectric in the middle. And it's big. We're talking about like the size of a warehouse. That's a lot of energy it can store. But you can cut this sheet in all sorts of different sizes. And when you cut it, it's going to change the amount of energy that you can store in the capacitor. So instead of talking about the total energy, we're going to use something that is constant no matter how much you cut it, and that is the energy density. So if I say that I can store, say, 5 joules per cubic meter, cubic meter, let me write that again. So if I say my energy density is 5 joules per cubic meter, then this parallel plate capacitor I have at the top of the screen stores 5 joules per cubic meter. if I cut it in half, it still stores 5 joules per cubic meter. Cut it in half again, 5 joules per cubic meter, so on. Even if I just take a sliver of this, it still stores 5 joules per cubic meter of volume. And so the energy density is very helpful in describing one capacitor, distinguishing one capacitor from another, relating them, distinguishing and yet relating them to each other. So how do you calculate energy density? Well, mass density was mass per unit volume. Flow density, when we talked about fluids, was, excuse me, not that one. There are a few different ways to do density. I gave you the traditional version of density, mass per unit volume. We're doing energy density the same way, energy per unit volume. So it's just potential energy divided by volume, which gives us an equation of 1/2 epsilon naught times electric field squared. Now, when you have a lot of energy stored up in a capacitor, there comes a point where that energy is high enough that you get a sudden discharge of electric energy. It's called a shock. And it can be harmful or even fatal sometimes. Capacitors can retain their charge indefinitely, even when disconnected from a voltage source. If you charge up a capacitor and then suddenly disconnect it, those plates are going to hold on to that charge. They will not let it go. Good example of this is a heart defibrillator. Except that in this case, we're not trying to harm or cause something to be fatal, but just the reverse. So the way a heart defibrillator works is you have 2 paddles, which are plates of a capacitor, which are then charged up. They build a lot of charge on it. You hit it, put the paddles on the human body around the heart, and then you discharge the energy stored in the paddles of the capacitor. And then what that does, I know it's an accurate description of a heart, but that's okay. So you have the 2 plates of your defibrillator that are around the heart, and it's going to cause a jolt, an electric shock, to pass through the heart. Well, what do electric shocks do to muscles in the body? An electric shock causes the muscle to contract. Basically, it pushes the heart, causes it to contract, starts pushing blood through the body again, thus hopefully restoring the brain functions, restoring life to someone who has died. That's basically the idea of what it does. So the heart defibrillator is a great example of a capacitor that has a very high energy density.